Okay, good afternoon, ladies and gentlemen. Welcome to this talk on C++ concepts for developers. My name's Hubert Matthews. I'm an independent consultant and trainer. I live in the UK in Oxford, next to the river. That's enough about me. I usually start with this question: why this talk? So it's always kind of, why am I talking about this subject? Well, one of the things I found talking to people about C++ and C++20, and I said, well, what is it you want most out of C++20? And they said, concepts. And I say, why? Better error messages? I think there's a lot more to concepts than just that. So this seems to be something that people want, but they're not entirely sure why they want it. It just seems like a really good idea and something they've heard about. So what I'm going to try and do is to frame concepts, going, well, okay, I'm not just going to do syntax. This is not a tutorial. This is about how they fit in the big picture and why you, as application developers, should be interested in concepts and what you can do with them. So we're going to have a few things here. So this is a broad talk. It's not a tutorial introduction. We will be looking at code. We will be looking at syntax. I will be telling you about some of the parts, but I'm not going to go through this is how you actually do them. That's a whole kind of separate other thing. I want to talk about the history of where these come from, because they're actually not very new. How does this work with other languages? Other languages have things a bit like concepts, and how are they different? So if you've seen other things in things like Java and C#, what is the difference there? Requires clauses and other places like that. What are we doing with types? So there's a whole relationship here about types and classes and interfaces and object orientation, and there's a sort of kind of bit of computer sciencey stuff going on in here we have to think about. How does this all fit together with inheritance and other things? And why should you care? You know, why do these people, these nice people at C++ Central stick this damn thing in here? Was it just to confuse it, or it just seemed like a good idea at the time? What can you do with concepts? What can you not do with concepts? And how should you design with them? So that hopefully that's going to give you an idea of how they are, where they are on a broad scale. It's not going to be an itsy-bitsy little thing, but we're going to see some odd things and some bits and pieces. Right, okay. Concepts have been around for a long time. Bjarne Stroustrup mentioned this in his book, Design and Evolution of C++ in 1994. That's 25 years ago. He's been trying to get concepts into the language. He got auto with the auto deduction in the 1980s, and then he had to take it out because C programmers hated it. So there's a lot of stuff that Bjarne has been trying to get in for a long time, and this is one of those ones. It was aiming to get into C++ 11, what was called C++ 0x at the time, and the point about that one is it didn't get in. And it didn't get in for a number of reasons. It was a language-based view, rather than, and had things like concept maps and some really quite complex things. It was an interesting implementation, but, and the but was a very big but, there was problems with compilation speed. There was only one compiler that did this, the concept GCC one, and that was about 10 times slower than normal compilation. That didn't look good. There were other problems with it. The technical wording in the standard, the so-called standardese for concepts, was bigger than the rest of templates put together. So this is like a kind of big major change. And they went, this is really not good. And it got withdrawn from C++ 11 at the Frankfurt meeting. So a little bit in the way that contracts have just been taken out in C++ 20. It just wasn't ready. People went, we've got one chance to get this in. We don't have the experience. We don't feel it's right. It got pulled. So it didn't get there. Right, okay, after C++ 11, there was like, okay, what are we going to do about this one here, these concept things? They're kind of nice. And there is this thing that of concept light. And there's several things going on here. So there was this technical specification, and that's what GCC, for instance, has implemented from version 6 onwards. There was a meeting at Palo Alto organized by Stepanov, who one of the fathers of the STL, and he invited lots of people through there, and they went through what are the concepts in the STL, and what were those things. So they went through that one. Well, we looked with this, we need to have this, etc. And that was kind of the basis of where the concepts TS. This is the minimal amount of stuff we kind of need. Having gone really big, they went, well, what do we actually need? Yeah, that was overreach, let's go to something else. That's what they did there. And it then became around requirements, not so much around language. For reasons because C++, because whatever. It didn't make it in C++ 17. Bit of a shame. It's going to come into 20. It was one of the first things that went into the working draft after C++ 17 in 20. So it's in there. There are some tweaks from the TS, but it's going to be in there. So what is it? What are we going to do? One of the things is that based around that sort of kind of Palo Alto view and Stepanov and other things, they think, well, actually concepts are maths. Or math, depending where you come from. This is something, it's a sort of kind of computer science-y view of the way things are done. It's an abstraction of mathematical concepts. It encompasses syntax and also semantics and constraints on types, etc. C++ 20 only does the syntax part, by the way. You can't do semantic constraints there. Based around axioms that you can't represent directly in the language. Well, okay, if A equals B, then you would expect that not A not equal B is always true. You can't express that. So these are some of the ideas that you want to get across in concepts in the sort of kind of big version of concepts of an idea, but you can't actually express in the language. So we have to think about syntax, semantics, and axioms. How would you express that the input to an algorithm requires it to be sorted? That's actually quite hard to express, and certainly hard to check, because actually you've got to go and do a lot of checking, and even if I give you two iterators into two different containers, how do you tell? It's completely, you can't actually check those things. So that's one view. It's not necessarily a view that I think is particularly helpful for application developers. It's one part of the landscape. Back to the Sufi elephant, with the leg and the ear and the trunk and the tail, etc. It's one part of the concepts jigsaw. There's another kind of view which says concepts are hard. They're difficult. You shouldn't try and do your own things. Application developers should stay away. And there's this idea that you shouldn't be writing your own concepts. You should use the ones in the standard library. You should use regular. You should use equality comparable and other things out of the standard. You shouldn't write your own ones. This is quite common amongst certain members of the community. I'm not going to point fingers, but it's one view that says, don't write your own concepts, because they're hard. Well, okay, you look at the core guidelines, core guideline T11. Wherever possible, use the standard concepts. Okay, well, that's fine, but what does that imply for application developers? Do you know what's there, and is it actually relevant to your domain? This idea that concepts are hard says, well, yeah, okay, that's fine when you're doing library stuff, but if you're an application developer, you're going like, that's not my domain. I don't write libraries. So my opinion, and it's just an opinion, that concepts offer fantastic new opportunities to developers, and if used well. So I'm going to try and see if I can give you a hint of what some of that might be. What can you do with concepts then, if they are such a good thing? What can you not do? They are syntactic constraints on types. Basically, when you've got template type name T, it's applying constraints to that. We'll see more detail coming up there. It allows us to put more domain knowledge into the application, into the language, and get it checked. What you might now have in documentation, you can now put into the language. Compilers don't read documentation. Developers probably don't read documentation. So the answer is, how do we get more checking here? How do we get this one here? So you can think of things like strong type defs, domain concepts. So avoiding passing just raw integers, you create some kind of domain type that represents something else. So instead of passing just a string, you pass a postal code or an ISBN or something like that. You're raising the level of what you're talking about rather than just pure native raw stuff. We're kind of trying to do the same thing here, but rather than T. Again, I said you can't express axioms, so you can't say that A less than A should never be true, or that if A is less than B and B is less than C, that implies A is less than C. There are things you can't do, so it's a limited set, but it's a useful limited set. You can also apply this to compile time values. So it's not just type name T, you can actually apply it to int n and other things like that, and template parameters, which will please some people a lot. A concept is a constraint on a type. It's not a type. You can't create a concept. You can't instantiate a concept. It's a set of constraints on something that already exists. For instance, you can't have vector of concept pointer because it's not a thing. It's a constraint on something else. You can have vector of object pointer and then constrain it to say, well, it has to be a vector of concept pointer. You can do that, but you can't create things of concepts directly. Oops, did we go back one? No. Contracts. Contracts, unfortunately, didn't make it into C++20. If you consider that concepts are constraints on types, contracts are essentially then providing some constraints on runtime values. So they have a very interesting complementary functionality. So they would allow you to provide some of the semantics. If you look in the standard, you'll find it says, oh, well, here are the types you could do that one, and then you've got some ensures and requires clauses, pre and post conditions, that tell you what things should do, when it's valid to call, when it's not, and those are often much more about contracts. So they're a very interesting pairing. Unfortunately, we're only get the concept part of this one in 20. We'll see later on how that will do this one. Okay, other languages. So we're going to have a look at C#, we're going to have a look at Java. What have we got here? C# has got something that looks a bit like this. It says, right, public class, gen T, where T has to be derived from I-comparable of T. It's essentially a similar kind of thing. It says, well, you can only provide me a T that meets these conditions. And they're syntactic conditions. It says, well, it has to derive from this interface. That's the kind of thing that you might want to do with C++ concepts. But there's a big difference here. There's a limit on what you can do with a C# version, so you can derive from this, you can use, there's other things, new, enum class, struct managed, whatever. There's only a few things you can say about this. And the reason there's only a few things you can say about this, because this is actually really a cast in disguise. It says, well, you can put that in there, and there, if you've got these certain constraints, then I'll do a cast, and inside you can treat it in certain ways. Because you can go, well, okay, if this one here has got gen T like that and it inherits from I-comparable, I can then call the methods on I-comparable because it's casted in the implementation. That's very different to C++. So one of the things about C++ concepts is it constrains what you can put in, but there is no constraint at all on the implementation. That's very deliberate. So in C# and in Java, if you have a constraint on this one here, what comes in also applies inside, because it's essentially an implicit cast. In C++, that's not the same. So if you've seen this before, you can kind of get a flavor. There's something similar, but it's not the same. Java, again, you can say, look, this thing has to extend number. So there's this exists in other languages, but in slightly different ways. Other languages, because they're object-oriented and they have an object right at the top, they're essentially doing some form of type erasure here. Right, so here's one of my key points, which is that how do you scale generic programming? So if you're programming with template type name T, you go, well, okay, I've got this third-party library which says T, what goes there? I have no idea. I have to kind of chase around for the documentation. If you're using something in Python, for instance, you go, yeah, it takes some stuff. I have to look at the names. I have no idea. I can put anything in there. And if I put the wrong thing in, what happens? It maybe falls over at runtime if I happen to call that particular path. So it doesn't scale well. And why does it not scale? Because it just says it's anything. Type name T. And if you've got, the more types you've got there, if you've got n types, you can go, well, I've basically got n squared, because I go, well, what can go here? What combinations are valid? What combinations are not valid? And you can't tell just by looking at type name T. If, on the other hand, it says a concept, it has to have this requirement. You go, okay, that's told me what's going on. Maybe my IDE can point me in the direction of going, right, you can't do that. Sorry, that's got the wrong thing. It's then essentially documentation that you've got to read, and the compiler's going to check it for you. That's one of the key things. Notice what happens as languages get bigger, as they get older, or they start used in more mature systems, is that typeless things start to get typed because of this problem. In C++, we're now at this point. JavaScript, Basically, yeah, you can call anything, and people have discovered that's a bit difficult, so they've introduced TypeScript, typing on untyped things. PHP, yeah, I can put anything in there. Oh, wouldn't it be nice if we just put some type traits on here, which just sort of kind of tell you what it is? And you can see this is a general trend as languages get larger and more mature, and you're trying to do more stuff. Java and C# generics, you've added these where clauses and wildcards, etc., because just T is just too wide. XML added in schemas, because is that really valid? I don't know. Oh, you've got some way of checking it. So concepts make generic programming scalable. That's one of the points I kind of want to make. Concepts are duck typing. If you've come across this idea in Python, it's probably where it first came from. If something looks like a duck, walks like a duck, talks like a duck, I'm going to treat it like a duck. And that's what templates do anyway, which is I don't care where you come from, what you are, what's going on, etc. Do you have the relevant stuff? And that's duck typing. Python does it at runtime. C++ does this at compile time. And what concepts do go, well, I can now do that checking at one point rather than the implementation. What's the difference? Well, if I have an implementation and I call something about 20 times and you pass the wrong thing, I'm going to get 20 nasty, incomprehensible error messages, this error novel that just goes on forever, yeah? If I have a concept that says, oh, sorry, you can't put that there, you get one message saying that's wrong, and here's why. That's a much nicer approach. We get much clearer interfaces rather than the, oh, well, what shall I pass in for this parameter? Yes, the thing that people are asking for, better error messages. We hope we're going to get better error messages. Compilers will get better at this, but if you try it, you'll find it at least tells you that can't go here, rather than, by the way, all these horrible things happen if you try. And it's based on the interface, not on the implementation. Currently, it's implementation-based. This is an interface thing. It allows you to capture domain knowledge. You go, well, what does it mean to be one of those things? I can now say, what does it mean to be an STL container? Okay, I'm only going to take an STL container here. And you try to throw something in that's not quite an STL container, it won't work. It allows for ad hoc and post-facto combinations that you don't have with straightforward OO. We're going to cover this in a little more detail later. This is an early form, really, of introspection. It allows you to be able to say, look, does this work? Can I instantiate this? It's a form of introspection of going, does this work? And it not fall over if you try. It's almost like you can go, here's some code that wouldn't compile, and just tell me whether it would compile or not. That's kind of a valuable thing. Other languages have things like eval that will then throw, yeah, Perl, try and evaluate this one, no, it's bang, whatever. But now we can go, if I did this and this and this, would that be okay? You can't do that now. This is what concepts are going to do. And you can then do it in an ad hoc way as well. So it's a form of introspection. The next step is we're going to get reflection, which is being agreed upon. The core model is there, but we haven't got the syntax for doing it. If you've used templates and you try to control overloading of templates using enable if and spin and all those other kind of things, you've now got a language-based mechanism rather than a hack. So those kind of enable things are a bit hacky. They work well at single point kind of stuff. I want to look at this one thing, but they don't work well. Actually, I need these 7 methods. It really doesn't scale very well to do that. They're built into the language, so you can now get compilers to do pattern matching for you. You can say, well, it matches this or this or this, and there's a defined order in which things happen. So you can write your stuff, yeah, if it's this case, do this, do that. You don't have to kind of do all this stuff with templates and jiggery-pokery, enable if, and then, oh, I forgot to do the not enable if version, and which one will get things, all that stuff which is possible but not very nice. And it's something that most application programmers probably wouldn't want to do. When I try to get people to use templates and we go, yeah, it's fine, but overload resolution control using this, it's not something where you really want to go. You feel like you're kind of doing stuff in the language rather than your application. I think with concepts you can now say, this is my application. I can say this in a way that actually is about my domain. You can also do some basic stuff here with things like if const expr and a concept name. So is lockable? It would be a concept here that says, does this have lock and unlock methods? So I can say, well, if you've got this, if you have these methods, and I can check at compile time. Notice that's a compile time check. I can go, if you've got this one here, you can call that. Great. It allows you to be able to do this kind of introspection in a way that you can't do now, because does this compile or not? I'm not quite sure where this quote came from, but it's useful anyway. We want more metaprogramming and less template metaprogramming. Yeah, we want to be able to do this kind of stuff, of be able to, can I do this based on this one? I want to do some special thing here, but I don't want to have to do the angle brackety thing. Yeah, it's just kind of horribly nasty with recursive templates, and then it's something that you kind of, it's a rabbit hole you go down, and you probably don't want to do it. A lot of application developers don't want to do it because they don't see it actually giving them any advantage. So the requires keyword is a way of saying, can this happen? We've now got this language-based approach to doing things. So if you kind of look at the history of where we've gone with this one, he started off with ways of trying to do template overload resolution control with things like the size of trick. If you're old enough to remember that, was a really horrible thing where you had functions and it returned something of size 1 or size 2, and you looked at the size of and you used a ... as a final thing to do all the other cases. Yuck. It was horrible. Enable if was kind of a better approach to this one, using SFINA. There's things in the experimental library of is detected, the detection idiom, Walter Brown and the like. That's a kind of along the way, but concepts actually make this usable. So we can start to do overload resolution that we couldn't do before. So we can now use this as a design approach in a clean language support rather than library hacks. So it gives us new stuff. Some basic stuff, so actually pieces of code, yep. Let's have a look at the simplest possible concept. So I've got a concept anything equals true. That says, yeah, this matches anything. That's the equivalent of type name T. I've got concept nothing that says, no, you can't put anything in this. You're always going to be wrong. So I've got at one end, yeah, I can do everything. The other end, I can do nothing. And I've then got a kind of range of possibilities in between, and it's up to you to decide what you want. So you've got a range of those things. We can do some stuff with inheritance as well. So actually you can override this ones or specialize them. But it doesn't require the underlying type to be changed. This is one of the key things about concepts, is you don't have to go and hack your underlying types to change them, to make them fit. It's one of the key things about templates. I don't have to go and edit the class of int to make it inherit from iDisposable or whatever you choose. Doesn't generate any code. It's purely compile time. So this is a very lightweight thing. Inside the language, inside the compiler, you don't have to do any extra stuff. And we can specialize it. So we might have something like try-lockable, saying, well, okay, this try-lockable thing is, well, it's lockable and it also has this try-lock part. So we can now specialize this. We can now start having hierarchies, and we can actually base our system upon, well, if you can match this, if you can match that, if you can match that, you can get the compiler to pick the right thing. So if you've got, instead of having hierarchies of object-oriented stuff, you can now use hierarchies of concepts and use the compiler to do some work there. Okay, here's a fun little diagram. It's an important diagram in many ways. So the two blue things on the left, type and class, those are closely related. They're tightly coupled, and they're to do with the way the language is done. So when you create a class, it has one or more types. Now, why do I say one or more? Because of polymorphism. If I have some inheritance, I have a base class and a derived class. The derived class can be treated like a base class or a derived class, so it can be treated like two in that particular case. So it has multiple ones, and each type can be implemented in multiple ways. That's why it's many-to-many. But that is something that you have no control over, really. That's built into the compiler, built into the language, it's tightly coupled, and if you go and change one, you're going to end up changing the other. Now, let's look at the other side. We have concepts. Concepts in some ways are completely unrelated to this. You're going, well, okay, concept is a constraint on a type. Yeah, I can do that. I can add it, I can take it away, I can do it. And notice I don't have to change the type in any way. If I used object-oriented inheritance, I'd have to go and edit the type or the class. I don't with this. I can go, yeah, it's one of those, Does it match this spec? Yes or no? It's loose coupling. And so this is really, this side of the diagram is what you as the developers get to play with. That type and class stuff is stuff that's already built into the language, you don't get to change, and is hardwired into the language. So that's why we have this looser flexibility with concepts. They're also kind of giving you a form of type erasure. What do I mean by type erasure? Type erasure says, I'm going to ignore some of the information about a class or type because it's not interesting to me right now. It's a form of abstraction. We're used to doing this in many ways. Interface inheritance with a virtual function. It goes, I don't care what class you are. I care that you are a pointer or a reference to this interface, and then when I call you, you'll do whatever the right thing is. Yes? Essentially, you've removed that information about the actual class of the thing, and you're going to say, I don't care as long as you have this method and I can call it. It's a form of type erasure. But there are other forms of type erasure. Operate around brackets. I just call this thing. Is it a lambda? Is it a function? Is it a function object? We don't know. And the answer is, we don't care, because at this point, we're saying, look, I don't care about the type, I care about what you can do. C out of X. Yeah, whatever. Whatever that X is, I don't care. Does it know how to print? Yeah, okay, go ahead, print. An iterator, you go star, you go plus plus on an iterator, you go, whatever, I don't care. Iterator is a fantastic abstraction in that sense. Concepts are similar to kind of type erasure. They give you a form of type erasure. They go, look, I don't care what you are. I don't care where you come from. I don't care who your parents are. I don't care anything about you, what you whatsoever, other than what you can do. So it's very democratic in that way. So with concepts, you're saying, look, I don't care about this one. With virtual functions, what you're doing is saying, I create my abstract interface. Right, okay. Now I have to go and edit my types so that the compiler can treat all these different types together as that one thing, so that we can do the type erasure, so they can be put back together so the compiler's happy. And then at runtime, I have to kind of go and call the virtual function, get the virtual pointer, and go and do some mechanism to get back the type that we originally had that I tried to get rid of so that the compiler would talk to it. This seems like an awful lot of work to have to go and edit something, to create this thing, go and edit the class, and just so the compiler's happy, and then recover it at runtime. When you discuss it like that, you go, yeah, that's kind of not very good. If I were to do this with concepts, I go, yeah, have you got these methods? Yeah, you're one of those. Great, call it. That's simple. No overhead. I can even inline the call. Great. So we're now very much more focusing on what the code does, what it's about. We don't have to go into all this procedural surgery. Right, other important diagram number 2. So the top part of this one is where we are with object-oriented stuff. You go, well, I have an interface here, so essentially you might think of time going left to right. When you have a client and server with an abstract, with an interface or pure virtual functions, both the client and the interface client and server depend on the interface. You have to have the interface available in order to compile. Yeah, you can't compile the client if it needs to call an interface and it doesn't know what it is. So you have to have interface.h included there. So what you get from this, though, is independent compilation. Because you can go, look, that client there, if it's trying to call something and pass a string where it wants an int, the answer is, no, it can't do. Because you can compile them independently. If I try to read an integer but a string was passed in the server, it goes, no, can't do. So I get independent compilation. But notice, I can only put together those things which are planned to go together. It's a whitelist. You have to have foresight to do this. Or you have to go and edit the classes to make it happen. If you try to take some third-party class and make it conform to this one, you either have to edit the class or do some form of adapter pattern.
I just wondered, you said independent compilation. When you have the base class, the client and the implementer can be compiled independently. They just have to be compiled with the interface. Right?
Correct.
Okay.
That was what I mean. Thank you, John. On the lower section, we're going to look at templates. Ignore the green concept for the moment, but if you just look at the blue boxes, you've got X, and then I have some some template, V, that takes this one, and I put them together. Notice that we have a different dependency diagram, because the first one we have, both of them depend upon having that interface around, because they have to compile against it. In this one, you go, well, look, and now the template and the thing that you're putting into the template are completely unconnected. So I can just take that and put them together, and then say, here, when I instantiate the thing on the right, V of X, does that work? Yes or no? This is why generic programming is very powerful. And this is why the STL works, because you can have vector of int. Because int knows nothing about vector. You don't have to change vector in any way. If you look at Java, their vector and their collection ones have to be Java lang integer. They have to be a boxed thing. You can't take primitives and put them in, because it has to be something that derives from something that will do that. So that's where the blue stuff comes from. But we don't get the independent compilation, because you can only go, look, when I instantiate this and I put those things together, oh, that's the error novel thing again, okay, because I can't do it independently. And this is also, you can see why templates are checked in two phases, because they go, well, I can do the bottom one, yeah, I can do this one, I can do all the non-dependent names, but until you tell me what the T is, I can't work out whether it's going to compile this. That's the two-step compilation for templates. With concepts, you go, right, essentially I'm applying what looks like an object-oriented interface to templates in terms of requirement. It says, yeah, that thing there, I'm going to constrain the type you can put in. So my concept C, I'm going, instead of having V of T, it's V of concept. If I try to put that in, it goes, nope, you can't do that. So what we've ended up with is kind of the best bit of this of the OO part of saying, yeah, I can constrain it rather than just being T and getting horrible error messages, along with this independence of not having to know about each other and not having to go and edit stuff and getting a genericity. So we've actually got the best of both worlds in some ways here. Okay, so maybe we're moving in the direction of object orientation. OO's been around a long time. Simulus 67, Norwegian invention, 52 years old? It's been around a long time. One of the classic OO books, 1995, was the Gang of Four books, Gamma, Johnson, Helm, and Vlissides. That's been around, that's a good long time too. That's been around 24, 25 years. There are lots of patterns in there. So you'd recognize the names of command, observer, iterator, strategy, and all the bits and pieces of those ones. You know what? Most of those are concepts. Because most of the stuff in the Gang of Four just says, let's introduce an interface. They go, yeah, well, we want to do this stuff, so instead of having this problem, we'll just introduce an interface. And they name that interface. So one of the things we learned from the Gang of Four is that names and vocabulary are very important. Because these days we just talk about observer pattern, and everybody goes, yeah, I kind of know what you mean. Rather than going, oh, here's a box and this thing in inheritance, blah, 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 and have to draw it out again. It's a chunk, a meme that we can use. But those memes and names are essentially can be mapped very easily to C++ concepts. But we can now do all that stuff that required us to have lots of object-oriented interfaces and inheriting from things and virtual functions. We can now do the same kind of thing, go, look, here's a concept, but by the way, can I just take this template, put that together with this concept? Oh, look, I can devirtualize this code because I don't have to add an interface. So I don't have to add an interface. I don't have to go and change my classes. I can put them together because it's just this calling that, and at compile time, you can work that out rather than at runtime, and therefore can do things like inlining. The networking TS, which is coming up, has got lots of these kind of names. Completion handler, things like executor. They're all concepts. So the interfaces that we often think about actually can map very strongly to concepts. This is why I think people that say, oh, concepts are hard, they're maths, and you should not do anything else, are missing out on this big trick. This is actually where I think really we're going to learn about this one. So named application level concepts are really important. Let's not think about them as technical or syntactic things. Okay, since we're in the world of OO, let's have a look at some stuff around role modeling. So the picture on the left-hand side is, if you ask people, yeah, I need to have some stuff here, I need a system for hospitals that has doctors and nurses and patients, Usually the first thing people come up with here's a person. I'm going to have doctor, nurse, and patient as subclasses of person. And you go, okay, that sort of kind of works. And then I usually ask the question, what happens when a doctor gets ill? Unfortunately, what happens when the doctor gets ill in this system is that you have to clone the doctor. Well, you have to create a patient from the doctor, kill the doctor, and then when the patient gets better, recreate the doctor and come back again, because these interfaces or these types are hardwired in for the whole life of the object. You can't change them. It's not dynamic in any way. And we can go through various things about this one here. In the picture in the middle, you go, well, okay, now I'm going to have person here, and person has all the functionality they may or may not have, and then I'll have interfaces instead. So I'll have an interface for a doctor and one for patient, so I can treat this person like a doctor, and then later if they get ill, I'll treat them like a patient as well. Yay! We can do stuff with dynamic stuff and things, well, okay, in dynamic casts, and have you got this interface or not? But these are roles. Notice I have to go and, if I add a new one, I have to go and, if I have some other thing like visitor or whatever, or some hospital administrator or whatever, I have to go and create the new interface. I have to go and edit the code, and maybe it works, maybe it doesn't. In the case of concepts, I go, it's a person, right. Okay, here's what I need a doctor to do. Here are the few things, right. Can you do that? Great, you're a doctor. I'll just treat you like that. Oh, I've got this other new role. I don't know. Can you behave like that? Okay, fine, done. I don't have to go and create the interface. I don't have to go and edit the underlying class. I don't have to do all this work, and I can do it all compile time. This is why I think it's something for application developers to look at rather than leaving this an isolated mathematical thing. Okay, enough of the bashing on about let's have a little look at some syntax. So here is the syntax for a concept, basic stuff here. Template type name T, so they're all templated. Totally ordered. Requires an A and a B, and you go, well, look, I want to be able to say that A less than B must return a Boolean, or something convertible to Boolean. I could then add all the other ones about A greater than B, but what I can't do is put a static assert in here that says that A less than A is never true. So that's part of our syntax of this one. We can only do syntactic checking. Axioms you can't check anyway, so how can you specify that end must be reachable for begin when I give you an iterators? It's not checkable at all. So you are going to need multiple things. This solves some problems. It helps you with the syntax. It does not help you with semantics, and it does not help you with axioms. You are going to need documentation. It is not a complete solution, but it's a damn good start. What can you check? Well, what you're checking really is, would this piece of stuff compile? So here's a little trap you can fall into. Right, so would this compile? What is it that you're actually testing? So on the left, I've got concept foo requires size of t equals 4. Okay, that's probably what you're thinking. Yeah, I can do that one. Then I go static assert foo of int. Well, int is size 4, yes. Foo of char. Char is not size 4, but that still passes. Well, actually what you're doing here is you're saying, is size of t equals 4 syntactically correct? You're not actually checking the thing. If you really want to check that condition, you actually have to put requires size of t equals 4, which is what on the right-hand side. And there you can see blah of int is true, but blah of char is not. So you are checking syntax. If you actually want to check return values, you need to do something else, and you need this nested require. So there's just one or two little corners and some fun pieces that come up. Just some variations on syntax. So this is a little bit of a history lesson here. So you can start off and going, well, this, at the top we've got template type name T. F takes a T. It's unconstrained. You can put anything there. I don't care. So that's the basic one. I have a concept foo, the simplest one, could be true, doesn't particularly matter for this one. My options, I can say template type name T requires foo of T, requires that this thing must be true. So I can constrain the template argument directly there. So that's the middle one there. That's one way of writing a concept. You can then move to the next one that says template foo of T. That moves the name inside. And it says, right, instead of type name, I'm saying, which is generic and everything, this is this thing here. So you've now got a much tighter way of writing. It's one of those. I could say template input iterator, T, or something along those lines. The TS, the concepts TS, then had an abbreviated form, which was controversial and not adopted. So we have void F, foo. Just pass a foo in directly. And you look at that and go, oh, that looks very short. I quite like that. I quite like that, but there are some problems with this one. One of the problems is it's a templated function, but you can't see it's a templated function. And there are differences between templated functions and non-templated functions. And so it was like, oh, grumble, grumble, grumble. Lots of people didn't like it. The killer argument was, if I do foo ref ref, if foo is just an ordinary type, that then maps to an R-value reference. If foo is a concept, that then is a forwarding or universal reference and maps to R-values or L-values. And you can't tell by looking at it. So they went, oh, okay, fine, right. So the syntax that came out was this constrained auto, so you can say foo auto, something like that. So putting the keyword auto in there, but then putting the concept in front, saying it's auto but constrained to this. And that's actually very generic and general, and we'll see some other uses of that. Concepts can be variables, they can also be functions. So on the left, I've got something here which is concept container, and then requires the following bits and pieces that says, oh, you have to have a value type inside there, you have to have a nested iterator, you have to have begin that returns an iterator. Notice, by the way, you don't have to say type name T, colon, colon, iterator here, because type name has been removed in a lot of 20, good. And you'll find that a vector meets that. On the right-hand side, we have the function version of this one here. So you can do those template variables or template functions. Fairly similar, it's a syntactic difference, but you'll need parentheses on the other one, just so that you've got both. Right, you can combine these things. You can combine concepts with conjunctions and disjunctions, with and or. So I can say, right, I have a concept integral is the standard integral stuff. I can have, say, it's unsigned, which is unsigned of that. And now I can say, right, concept unsigned int is it's an integral and it's unsigned. So I can combine those things. And now you'll see that unsigned int is definitely one of those, and an int is not an unsigned int. And I can do static checks and static asserts, and notice it's checked at compile time. That's conjunction. Everybody goes, yeah, that's great, I can do that one. Another thing you can do is disjunction, which causes a certain amount of controversy, but I'm going to show you anyway, because I think there's some uses for this. What happens if I'm trying to write a library for saving things, for doing archiving of stuff? Well, I've got some classes that have a save method and some that have a dump method. Well, I could try and write one method that would do this one and do the type stuff and put some other things, or I could write the library and put adapters in front of it. There are various options here. But maybe what I can just do is go, well, look, archivable says you've got a save method or you've got a dump method. And then I can go, right, okay, this S, which has got save, is archivable, and the other one is as well, because it's one or the other. That's actually quite simple. The other ways of doing this with adapters and everything else look like there's a lot of mechanism. This actually kind of says what I want. Well, I want that one, I want that or that. And to me, I don't think that's unusual. It's actually something you can't do with OO, because with OO you go, well, I can't have an interface. I can drive from one of those or one of those. There's no or in object-oriented inheritance. So I can now. So the stuff on the left is just repeated from the previous slide. The stuff on the right, there you go, archive. Well, if you have a save method, call this one. Or I could say, if you have a dump method, call this one. So I can now override based upon those concepts, which is kind of nice. And that's why it's const has save auto, because this is a constrained parameter. Archive2 says, well, actually, look, no, I'm not going to get the compiler to do this one. I'm going to be able to say, I'll just have archivable, and inside I can do if const expr. I can do a runtime, I can do a compile time check, and it goes, yeah, I could do that one here. If it's savable, call the save method, otherwise called dump. And notice that that can be inlined, it's compile time, I don't have an if statement. So I have eliminated that overhead. So this is a way of avoiding things like adapter pattern. Okay, you've got existing code. You're not about to write all new stuff. What do you do with some existing code? How do you introduce concepts to existing code? And there are some considerations. You go, well, okay, first of all, no bare T. If it says type name T, you're going like, well, what do you actually mean? Do you really mean T? Or do you mean something else? Do you mean it's got, yeah, but it's T, but there's obviously some requirements. So let's work out what that might mean. What are you doing there? Pass domain parameters rather than integers as an example. But you can take an outside-in or an inside-out view. So the outside-in view is a domain-based view going, what are we doing here in terms of abstractions? What's generic? What's this really about? If I look from outside and don't worry about the implementation, what kind of things are we talking about? So you can start producing domain-level concepts. The alternative approach is, well, you have your head inside the box and go, well, look, I need to be able to call this and that. Okay, I'll just have the requirements that it does this and that. So you take the implementation and you push it outwards. That works, but again, you're lacking abstraction when you do that. You end up with a minimal syntax-only based one rather than any form of generic concept. And this then leads us to another parallel with OO, which is in object-oriented patterns. There are patterns you use for design and some you sort of kind of discover as you're refactoring. Some of the design ones, you go, well, look, I'm going to design with this. If I'm using composite pattern, it's usually because I'm going to design with composite pattern right from the start. That's kind of how I build my system. Observer can be another example of that one. And you go, well, I have broad constraints here, a broad concept with multiple constraints. They represent something in the domain, and they have an obvious meaning. If they don't have an obvious meaning, then really you need to work out what it is that you're actually trying to do. But then you might also have concepts that you've discovered in a more sort of kind of technical way through refactoring. You go, well, okay, I've refactored this thing out here, and it's a very narrow concept in the way that adapter pattern is sort of kind of something that you don't want to build your whole system out of adapters. It ends up with just a kind of glue upon glue. Yeah? Okay, so that you may well find the discovered ones what happen when you take existing code and add it. What about unit testing? Well, you could do unit testing and you put in, okay, I need to put in a virtual interface here because I need to use Google Mock and I want to be able to have a substitution point, etc. If I just use a template with a concept that says, right, I need a database here and all it needs is write, all I need to do is just provide something that has write. It's that simple. It's document what it is. Well, that's all I need to do. I can break my dependencies more easily. I don't have to go around and start using heavyweight libraries and virtuals and all sorts of other things. I should just be able to just go and do that. Okay, one or two things that about concepts that you can do with concepts you can't really do with other things. This constrained auto. So instead of just saying auto X, I can go, well, look, it's some concept, auto X. Because if you're just using auto as the return type of a function, it says auto over here, you're going like, what's that? I've got to kind of dig around. You go, well, yeah, that's fine. Whatever that is, I just want it to be able to do this stuff because it becomes, then I don't care what the exact type is, I just care what it can do. So you're now programming in terms of intention, in terms of interface, and rather than in terms of type and class. This disjunction of concepts is something that you can't really do with OO at all because you can't do this multiple inheritance, well, it could do that or that. You can constrain non-types, so you could actually have an implementation that says, well, requires n less than 10 because this is the small object optimization version of vector. If it's bigger than that, whatever. Hierarchical constraints. So there's a whole hierarchy of things like iterators. Iterator types. You can actually have different concepts for input iterator and forward iterator and random access iterator and have different functions called depending on those. You can't do that so easily with OO otherwise, other than building all this stuff with inheritance, but then you've kind of lost all the advantage of having just being able to use a pointer. Briefly, there are some C++ core guidelines about concepts. I'm not going to repeat them all, but just to point out that this is sort of kind of the idea of no naked T, so specify template parameters as concepts. Use standard concepts where possible. That doesn't preclude writing your own, as I said. Prefer concept names over auto for locals, like that one, my concept. And prefer this shorthand notation for simple ones. So that's back to this guy here, way back when, the one at the bottom here, rather than the template one, use that simple shorthand one. That's what that's talking about. In terms of defining it, don't just have concepts without any form of meaning. Don't just make them in terms of technical things of it. It has an operator plus. Nothing kind of like that. Look for a complete set of operations and constrain that whole thing. Specify axioms even if you can't put them. There are other ones, and I'm not going to go into the details. You can go and dig them out. So, summary. They are there to give you, so concepts are there to allow you to express domain-level concepts. They are limited to syntax, and they limit what's coming in. They do not limit implementation. You should document your semantics and axioms as well. I think that these make generic programming scalable, and I think they are a very useful alternative to using OO, and they make patterns more efficient in terms of generic way of doing this one here. And I think it's a fundamental change in the way that we write generic code, and they're a lot more than just template error messages. Okay. Any questions? And yes, no, am I?
I have a serious question. I want to talk to you later, but this is a serious question. In a correct program, if you remove all of the concepts, is it still a correct program?
If I remove const from a program that's correct, is it still correct?
I'm asking you, I said, not const.
Yeah, well, no, I'm making a serious point as well. I can get, if I took away all the const, if I took away all of the concepts, if I took away all of the types, assembler has no types at this point.
So the answer to const is no because of overloading. So if we take out overloading on concepts, if we take that off
Right.
the table, and all they are is constraints
Yep.
on allowed types, if you take out all of the concepts, is it still a correct program? Does it do the same thing?
Probably because you've got no overloading, because what this is doing is helping you to make it scalable. Python still works. Python just does this at runtime, essentially, because it says, well, just it can take anything. It's type lane T, and you just put it in, yeah? And it's a runtime thing. I'm getting some view. So there's a view here that maybe that answer is not without controversy. We'll have a chat later. Any other questions? Yeah.
Concept seems like a nice thing to constrain templates, but to upgrade already existing interfaces, that's sort of more tricky because you need to move implementation into a header file typically.
Yes, it's not a gimme in the sense of, yeah, I can just do this and throw concept everywhere. Yeah, you're going to have to think about this. But what I'm trying to do is to get away from this idea it's somehow this sort of religious mathematical thing that's over in the library in the standard, and developers should just go, yeah, we'll use that stuff. No, use it. It's there for you. That's what I'm trying to say. It's not something that should be reserved for just a few people. I think it's much bigger than that, much more important than that. But you're right, yes, it's not going to be just kind of, yeah, I need to do this one here and OO interface because you've got implementation that's hidden. You're going to have all the overhead of moving stuff into template files, but then what do modules do then? Yeah, we're going to have some fun over the next few years with this. Anybody else? Okay, thank you very much.